Okay. So again, we're recording. And I know the last recording actually went up, got taken down, and should now be back up. So double check that for me if you could at some point. So what did we talk about last time? The idea of, well, first of vectors, right? We're starting to build an arithmetic around vectors. This new type of quantity. It's got its own rules. The idea of multiplication, or let me back up. The idea of addition and scalar multiplication look pretty similar to what we're used to. When we got to the idea of multiplying two vectors together, we had to hit the brakes and say, what's going on here, right? What does this look like? And so the first kind of version we looked at was called the dot product. And we saw that the dot product was motivated by what in the real world?
Work.
Yeah, by work, which is the force times the displacement. So we had to figure out what that is, and it turns out it's not just the force and the distance it went, but it's the component of the force in the distance it was displaced, in the direction that it was displaced. And so this is kind of like a directional multiplication. Which means that higher values, because it's equal to really, the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So what that means is that higher values imply that, F, S are pointing in the same direction or in a similar direction. And negative values imply like opposite directions. All right, so we might have something like this would have a high dot product. Something like this would have a very small dot product. And we learned one other like really nice property about this directional multiplication. If they're pointing in the same direction, it's a high value. If they're pointing in the if it's a small value, the dot product, they're pointing in opposite directions. What was the third kind of thing we discussed last time?
They could be orthogonal.
Yeah, if they're orthogonal, then we know that the dot product is what?
0.
Yeah, is 0. This is the case if and only if A is orthogonal to B. Okay. Motivated by work, directional multiplication. The value of the product tells us kind of what's going on. It's a really, really nice way. You'll see that a lot of the stuff we do later in this course is by hand computationally pretty, pretty extensive. Excuse me. So, I might be dying. Hold on. Send help. All right. So, it's computationally quite a lot of work to get into certain things we want to do. We might say, hey, it'd be great if we could integrate in this way. It would take a lot of work. Why don't we first see if these two things are orthogonal or not? And so it's very easy to do to check the dot product of two vectors to see if that's the case before you even jump in and do something. So that's kind of our top use of the dot product. Okay. It shows up in theorems. It has all sorts of applications itself. But mechanically, we'll use it like that a lot. So put kind of a star next to that theorem there. And that we know that it's really equal to the product of the magnitudes times the cosine of theta using this typical multiplication. And it results in what type of number? The dot product ends in a...
Scalar.
Yes, thanks. And who was that? Sorry? Courtney, thanks. Dot product ends in a scalar, or results in a scalar. Okay, so you start with two vectors, end up with a scalar. There are some nice analogs to linear algebra here. I'm not going to assume that we have taken that or even plan to take it necessarily. I think everybody should. But we're going to kind of do some hand waving with some of this stuff. But just to know that these things have matrix equivalents that will pop up. So you'll see these again and again in different fields. So anyway, that was the dot product. And what we're going to do now is extend and kind of play with this idea a little bit. Because now that we're playing with vectors, what I said at the start of the class was that vectors really simplify a lot of the geometric problems that can arise. Okay, this theorem right here is one of those things that makes that job a heck of a lot easier. We're going to look at the cross product later today. That will also help. But while we're here playing with the dot product, I wanted to talk about projections, and this will come up a lot. A lot of times what we want to do is project a vector down onto an axis or onto another vector, right? What is the shadow of this vector on top of another vector, right? So if we have a given force here and here, and I'll call this A and I'll call this B. You'll notice A is not flat, it has some angle to it. If I project the vector B down from the top, right, perpendicular, or I draw a perpendicular to the vector A, we have this angle theta between A and B. What do we call this length here? How could you describe to me the length of this side using the information I've given you so far?
That's the projection of B onto A.
That's a projection of B onto A, yes. And if I were to ask you, what is the length of this side of this right triangle that I just made up, this projection?
Isn't it like B cosine theta?
Yeah, it's B cos theta. That's right. But not B the vector, right? We're talking about B the length.
The magnitude of B.
The magnitude. Right. The magnitude of B cosine theta is this guy here. So this is the magnitude of B cosine theta. Right? Why? Because cosine is adjacent over hypotenuse. And so if we solve for that side in terms of theta, we get hypotenuse times cosine theta. So that's why I said review your triangle trig just so that this stuff isn't too terrible. So that's right. This is B. This is the magnitude of B times cosine theta. So that's the length of this projection. And what we call this is the scalar projection, or the component of vector B on vector A. Okay, so the component of B along vector A is given by the length of this side here. So we say that, let's write it out a little bit more formally because I want to manipulate this a little bit. Okay, so what equation do we have that relates vectors to magnitudes and cosine and the angle between them, but that theorem from the dot product, right? We know that A dot B is really magnitude of A times the magnitude of B cosine theta. And so if we're saying that the component is equal to this piece right here, then one way to write the component of B on top of A, this length, is to just divide both sides by the magnitude of A. So it's equal to the dot product of the two vectors all over magnitude of A. So you've got two definitions. You've got this one, or you've got this one. The elegance, the niceness of this guy here is that I can find that component without needing to know the angle between the two vectors. Right? I can find the length along that vector without needing to know the angle. That's amazing, right? That's just because Cartesian coordinates work the way that they work. So you can see how this already is like trivializing a lot of geometry problems that would have been thrown at you over the years, just to be able to find the length of that shadow there. And so I'll hold that thought for a second. So the component is the length of the shadow of B on A, right? And this holds up even if they're pointing in the opposite direction, okay? The algebra holds up. And so the vector that points along A with this magnitude is called the vector projection of B onto A. So in other words, if I have this vector B, this vector A, this vector here starts at the same tail and terminates where the shadow ends. This is called the projection of B onto A. And what type of quantity is this? Being drawn as an arrow in space? Is that a vector or a scalar?
It's a vector.
It's a vector, right? Whereas the component, the scalar component, this is just a scalar. Not just a scalar. It is a scalar. Here, this is a vector. So what do we know about this projection and why do we care about it? Okay, I'll tell you that in a second. So what do we know about this projection? Well, it has the magnitude which is the magnitude of B cos theta. And it's pointing in the direction of A. What did we learn about last time? That we can always get a guaranteed vector in the direction of a given vector. We can define a vector that's in the same direction as one that we have. Here's a clue. It starts with unit and it ends with vector. It's called the unit vector. Okay. So the unit vector is what? A vector in the same direction of the one that we care about, but with a length of 1, right? Length of 1. Why is that nice? Well, because then I can scale it to whatever I want, right? If it's got a length of 1, whatever I multiply it by, scalar, it becomes that length. So here, it's pointing in the same direction of A. So what that means is this vector, the projection of B onto A, is really the magnitude of the component, this magnitude of B cos A, so that length, cos theta, scalar times the vector A divided by its magnitude, the unit vector in the direction of A. So there's a nicer way to write this, which is again to kind of get rid of the cosine. And how we do that is to recall that this length here is what we came up with up here. Right? We can get rid of the theta by replacing this with that. This is really the dot product divided by the magnitude of A. All times A over magnitude of A. Get rid of the theta. And then just rewrite this. All right, I've got the dot product over this magnitude squared all times A. Okay. You might be thinking to yourself, why is this cool? I think it's cool in its own right, the fact that we can come up with this vector without needing to deal with the angle, right? That's pretty amazing. But B, the reason that we care about this is that we're about to embark on doing calculus in R3 and in Rn, right? So gone are the days of just caring about when I scooch over a little bit on the x-axis, how does the slope change in the y-axis, right? We're going to go way past that. We're talking about when I move in this direction on a surface, right, with a given trajectory, and I'm going to be summing up areas or finding, the slopes of tangent planes, the partial derivatives in different directions. We need to be able to talk about these vectors pointing in the same direction, being projected onto each other. It gets kind of crazy to orient yourself. So this is like one of those key skills. And it's really nice to have things that work out with nice calculations that are simple to do. And A dot B is really simple to do. Finding the magnitude of a vector is really simple to do. What we're going to do later, the cross product, it's simple enough to do, but it's a pain in the neck. And there's a lot like that in this course, just because it's that much more complicated. But this is one to have in your back pocket, okay? It can simplify a lot of problems that you're working through, just to take the projection, just to find, how long that shadow is of B over a given vector. And then if we want to actually turn that into a vector for some reason, or find, the component of, like from work, find the component of the force along the displacement, this is how you can find it without even knowing the angle, right? So that's pretty cool. And so with that, there is the example at the end of the text section on page 852, which has a walkthrough of a work example, which I'd recommend. It's a pretty canonical example for this, and I have no commentary on it outside of what's there, so I'll let you guys enjoy that. But it's nice for the physics-minded folks. So we have the vector projection of B onto A. We have the scalar projection, or the component of B along A. And while we're here as well, I'm going to quickly just talk about the direction cosines. Did we have any questions about the projections before we move on? Okay, again, just a nice application of the dot product, which is this new operation. And, oh, where did that thought go? Oh, and we're going to need to have some tools to orient ourselves when we're talking about partial integration, partial differentiation in the direction of a vector or a space curve, something like this, right? It's one of those helpful tools. So, I'm not going to cover this too in depth either. The direction, not direction of, direction cosines. And this is really the cosines of the angles a vector in R3 makes with the coordinate axes. Why cosines? Why do we care? A few reasons. What's nice about cosine and why, people were trying to tell you this is an even function all these years and why we care about even functions. One of them is because it doesn't matter the sign of the angle, it's still going to give you the same cosine, right? So if you flip it. So that's nice, and that results in some nice algebra, some nice identities. This is only really something, too, that works in R3. It breaks down in higher dimensions. So essentially, from a given vector A, we'll say this is, A1, A2, A3, or we could write it in its component basis vector form, rather. A2j hat plus A3k hat. See that if A is a vector, and so is I hat, right? What was I hat, j hat, k hat?
They were vectors.
They were the, sorry?
No, basis.
Yeah, the basis vectors, right?
Same thing.
Yep, for sure. This is the 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. So they're vectors. They have magnitude 1. That's really nice. So if I take my vector A, whatever it is, and I dot product it with a basis vector, I know that this is really the magnitude of each of these vectors times the cosine of the angle between them. And I'm actually going to change this theta to an alpha because it's a quote-unquote special angle. Magnitude of I is what? 1. So this reduces to just be magnitude of A cos theta equals A dot I. And so what does that tell us? Is that cos alpha, the angle that A forms with the x-axis, is given by this divided by the magnitude of A. Okay, so you dot it with the basis vector. And this should make some sense, right? That really you're dotting I with the unit vector in the direction of A, if you see that here. So it's how far in the x direction did it come over? That's the cosine. I can afford a sketch here. So if I have some vector A, it's pointing out here. And again, remember I told you last time to associate each point in space as really also being the end point of a vector. And so what we're saying here is that the angle that this vector makes with the x-axis, which is tough to see from this angle, but this is that alpha. Okay, should really be, we could look at its projection over here. Actually, let me redraw that, because that does not reflect what's actually going on. We had this projection over here. It'd really be like this here would be alpha. Okay, and so really it's taking the unit vector of A in the direction of I. Okay, taking that dot, and then that's the cosine of that angle alpha. And so likewise, by similar logic, this is the case with beta, the angle that the vector forms with the y-axis, and that's A dot J all over magnitude of A. And of what we call gamma, which is A dot K, magnitude of A. And these are what we call the direction cosines. And we can simplify this a bit further too, right? What happens when you dot a vector with the basis vector? Well, the component that's non-zero on that direction is going to stay, and the other two are going to drop to 0, right? What happens if I dot A1, A2, A3, dot with 1, 0, 0? I'm going to be left with A1 times 1 plus 0 plus 0, right? So we just get left with A1. So you could really simplify this to be A1 over the magnitude of A, A2 over the magnitude of A, A3 over the magnitude of A. Quite a lot simpler. The z component divided by or scaled down by the magnitude of the whole vector, that's the cosine, that's the scooch in that direction of the angle that it forms with that axis. Let me see if I have a worthwhile example here. Not really. I have some nice properties here, though. And the first is that if we create a vector with cos alpha, cos beta, cos gamma, it's a unit vector. We also know that the square of the cosines equals 1. And I'm not going to prove these. I'll show proofs of exciting ones, okay? But ones that are not that fun, we're going to say, I would never lie to you. Just, you can trust me, or you can look it up later. All right. So, this is a univector, and it's in the direction of A. And so another way to write A2 is to take the magnitude of A and to scale by the cosines, the vector with the cosines. Because what is really the cosine of an angle? It's how much it's scooched over in that direction by being off that much. So that is some nice things about cosines since we're in there playing with the dot product. Okay. Questions there? Okay. In this course, we're going to do more worked examples than we've been doing. I tried to frame and reframe again that we're kind of playing in a new space. There's a lot of just information to get out there, okay? But we are going to be working through more problems during class time. So let's do one example here. I think we've got time. So just to practice with these definitions, find the direction cosines and the direction angles if we have time. But maybe this will help us kind of see what's happening here. So finding the cosine of the angles, how far this vector has been moved away from the coordinate axes. So we know that cosine of alpha, the angle it forms with the x-axis, is going to be given by what? The x component over the magnitude of A. Well, what's the magnitude of A here? Two squared plus 1 squared plus 4 squared. (16, 17, 21). So this is 2 over radical 21. So then how about beta and gamma?
One over radical 21, and then 4 over radical 21, right?
Yes. Right. And so if you run these through, again, you can check this after, but you take the inverse cosine of 2 over radical 21, inverse cosine of 1 over radical 21, and of this guy, and you should end up with 64.1 degrees, 77.4 degrees, and 150.8 degrees. Okay, so we've got their cosines. Got their cosines. And then we've got their angles. So we have a bit more information, quite a bit more information about this vector, right? Kind of a different perspective, which is super helpful. Okay. Questions on that example? How to use these equations? Not too bad. All right, cool. So let's move on to the next kind of version of what I said was our next take on vector multiplication. And I'll say too, if you're looking for a better than I can draw and a different interpretation of this stuff, a few years ago I remember watching you guys know 3 Blue 1 Brown. Have you heard of that channel? Seeing some head nods. 3 Blue 1 Brown. He was one of the guys that originally started Khan Academy. He's gone off and done his own thing, and he has this amazing Python coded engine to do math visualizations that you just can't draw. And he also has some unique takes. He's been a math educator for a long time on high level stuff, which is really cool. So if you want to go check out, there's a lot of blurred lines between linear algebra and multivariate calculus. I highly recommend watching some of those videos, as it can give a different insight. It's not to say to replace this, because I think he expects a certain familiarity when making those videos, but they are truly great, and he's a great teacher. He knows how to explain things well. So I say that because there's a completely different interpretation of dot product and cross product than I'm going to give you, because it assumes a bit of familiarity with linear algebra. But for vector multiplication, I wanted to kind of break down what we've been working on. The one was the dot product. A dot with B, and it ends in some scalar C. And it's really a measure of how much are they pointing in the same direction. It told us that the dot equals 0 if and only if A is perpendicular to B, which is really nice. And it's nice with theta or no theta. We can do a lot. And it ends in a scalar. The second form of vector multiplication, and again, I'm using that word pretty irresponsibly, okay? It's called the cross product. And we use this symbol, the old school times, to represent the cross product. The motivation for this, there's a few in the physical world that are nice, but a lot of them are kind of high-level stuff that comes later. One you can think of is torque, right? So turning a wrench or closing the door from a farther out point. Turning a wrench is the most kind of salient one to me, because as you apply force in this clockwise direction, right, what's happening is that how hard you turn it is telling you the magnitude of the force of the bolt going through the wall or whatever the thing is that you're driving it into, right? So cross product is that idea mathematically, okay? So the torque crossed with the length of the arm gives you how much force is really being applied outward in a perpendicular direction is the key thing here, right? So the wrench is 90 degrees to the thing that you're turning, but the thing you're turning is really being forced in that orthogonal direction. So the motivation is to get a vector that is orthogonal to both A and B. Why do we want that? Well, A, so we can talk about torque. That's a really important force on its own. But also when we're talking about orienting ourselves in space, there's a lot of structures that are defined by that perpendicular vector to the surface, okay? So what direction is a force flowing through a mesh, right? If I want to capture that moment, there's the perpendicular to the mesh, which might not be a perfect square shape, right? It's going to have its own surface to it. There's the perpendicular to that at every single point, and we can use that to measure the components of how fast a stream is flowing through it. These particles are flowing through some, foil screen, whatever it might be. So we want to know what we call the normal, which is the perpendicular vector to a plane or to a surface at any given point. So using the cross product is a way to get there pretty easily. Not that easily, but it's a guarantee. It's a guarantee to get a normal vector. One nice example too is planes. Just just a straight sheet of paper in space. The equations that define planes, which we'll get to in the next section, they're defined by the vector that's normal to them, okay, or perpendicular to them. So really great way to either find what that normal vector is, that perpendicular vector, or to go and find it for a given plane. Why do we care about planes? Well, we care a lot about tangent lines in Calc 1 and Calc 2, and now we're going to care about tangent planes, right? How something approximates a surface by using a plane to lay on top of it for optimization problems and all sorts of things like that. So this is an important idea, is what I'm trying to say. Because it is mechanically intensive, it's a lot of kind of grunt work, and there's a lot of places for arithmetic errors. So I want you to just know that it's worth it, okay? It's worth the effort, and we're going to keep using this idea throughout the entire course. So how it's defined. It's nice to have the geometric intuition while we can, so we'll use it. A and B with some angle between them. This arrow is actually really important. This signifies the right-hand rule. Does anybody remember what the right-hand rule is? Okay. So the right-hand rule is what we use to orient ourselves. If the first group of people that came up with this were left-handed, we'd probably have the left-handed rule. So it is arbitrary, if that's your next question. But it's one that we stick to. So we say that the right-hand rule is what dictates a positive direction. So this is something I was confused about all through grade school, is why is counterclockwise positive, right? Why is what seems like backwards from the rest of the world, how we tell time, why is this positive? It's because of the right-hand rule, okay? And so what it says, and now that you know about a three-dimensional grid, is if you put your hand, I'm going to make myself a little bit bigger here because I'm doing this just with my hand. So if you put your hand on your desk, and you should all do this right now, okay? Put your hand on your desk and put your the edge of your hand with the pinky out where the x-axis would go on your sheet of paper, okay? So pointing out to the right. And then you curl your hand towards where the y-axis would be, and then see where your thumb's pointing, okay? That's the positive z direction. And so what we do is we say, well, for a given vector, if the smaller angle, I can curl my fingers towards it in this way, then this is the positive orientation. And so that means the outward vector, the 90-degree vector to that, is going to be where your thumb's pointing. Okay. So again, you can kind of just visualize if my desk is the XY plane, how I've done grids my whole life. Counterclockwise is the positive direction, which means up is positive for Z. Does that make sense? Okay. So that's the right-hand rule. So I think about this. They have a thing with this as well with the 3 fingers. I find the curling the hand is a lot easier to picture, but you can picture it like this with I, J, and K as well, and this will keep you positively oriented. Okay, I, J, K. So why that's important is because what I said before about this being kind of a laborious version of multiplication, it actually matters what order that you multiply in, which is something that you've probably never had to deal with yet, right? For your whole life, it was 2 times 3 is 3 times 2. What are you talking about? Right now, it's A times B cross product is not the same as B times A. It's actually the opposite. So there's huge consequences to that, okay? So, we get none of the liberties of regular multiplication with cross multiplication. So use this to orient yourself. This is specifically for when the smaller angle going from A to B, this is the angle that we're talking about. And this is the first vector in the operation. So we say that A cross B, okay, is done in this order. And so how we define it, there's a few ways to go about it. One way so I'll just say here, order matters. Order matters. Used to orient the positive direction, and always use a smaller angle between 2 vectors. So I'm going to draw another picture here just to kind of free up some space. So here's A, here's B. If we think of continuing these vectors out, or I sweep up vector A up here and B over here and create this parallelogram. A cross B is really the area of this parallelogram. But there's a catch. It's only the area of this parallelogram if this is A and if this is B. Okay? If it's the other way around, or that the angle is larger than 90 degrees, it flips, right? And it becomes a negative area. So I want to say, in quotes, it's actually the signed area of this parallelogram. And that's what its magnitude is, right? But really, it is a vector whose magnitude is the area of this parallelogram, and it points, I'll say orthogonal to the plane that A and B create or lie in. So if you think about 2 vectors pointing in any direction, it doesn't quite matter. You can draw a plane between them. You can make a parallelogram between them. And so whatever that is, I can find this vector that has magnitude of the area and it points 90 degrees away. And so your question might be, well, it's 90 degrees to a plane. There's two possible vectors, right? I could have it be this one, or I could have it be this one. Which is it? Well, this is the opposite, okay? And that's why the order matters. So if you switch the order of A and B, it actually goes in the opposite direction. Okay, so this is also B cross A. So there's like a little AKA here. So depending on how you're oriented, just kind of keep that straight and just be aware that's something you need to know, that it will have a sign. All right, how do we do this? Because I just keep drawing pictures. I've told you what it is, how to think about it. I'm going to show you two ways to calculate it. Please use what is easier to remember for you. I'm always going to allow a notes sheet on an exam, so you don't have to really memorize this, but I think you know at this point as well. Memorizing doesn't take too much, and it's really helpful, so you don't have to recreate the wheel or be flipping through pages whenever you want to take a test or work on a problem. So whatever seems more reasonable to you. So I'll show you the way I learned it. Call it the old school way, the nonlinear algebra way. So how to calculate. So I gave you that drawing so that I could also do some hand waving and not go through all of the geometry on how this is calculated, okay? Know that this is where it comes from. The fact that we're finding the area of this parallelogram, this is how we get these components. So A cross B is the vector given by A2, B3. And this is if A is A1, A2, A3. B has components B1, B2, B3. So it looks like this. A2, B3 minus A3, B2. That's the first component. Okay. A3, B1 minus A1, B3. That's the second component. And right now you say, no, Mally, I'm having too much fun. Please stop. A1, B2 minus A2, B1. That's the third component. Okay, so this is what I was taught when I took multivariate. I was taught just memorize it. Don't ask questions. Just do it. It worked out pretty well. It is kind of cumbersome, but one way that you can remember it, and again, I say this because we're going to do this a lot. Typically, long, laborious formulas, we try to just kind of outsource to the calculator. This one, not so much. You're going to want to be able to do this. You're going to want to be able to do it without making mistakes. So one way to remember this is that you see that the component in each of these that's not represented is the slot that it's in, right? So you don't see A1 or B1 in the first component. You don't see A2 or B2 in the second component, and you don't see A3 or B3 in the second component, or in the third component, right? So you don't see these guys, you don't see these. So that's how you know what components should be there. Again, it comes from a whole chase of algebra through finding the area of this parallelogram. And what was I going to say about that? Oh, and just remembering the order of these things. Again, just memorization. You could make a flip card, look at it, 3 times a day for the next week, and you'd have it. There is let's try one with that, and then I'll show you the way that you can use some linear algebra in a kind of hacky way to get there. So find A cross B. If A is... What? I had a good one. Okay. If A is 2, 1, negative 1, and B is negative 3, 4, 1. And then we'll find B cross A. So try using the formula yourself. I'll let you kind of get set up, and then I'll jump in and work it out. Just kind of get used to this. Two is 1. 8 plus 3 is 11. Okay. So, not too terrible. Obviously, kind of laborious. Easy to make mistakes, easy to drop negatives, all that fun stuff. So, just take it slow. You'll get faster over time. I do think the second method I'm going to teach you, while it's kind of hacky, works a little bit better, works a little bit faster as long as you get used to it. While we're on the topic, B cross A, what would this be? Easy mode here. I'm not making you do it twice.
Just negative everything.
Negative everything. That's right. We try to stay positive when possible, but this is negative everything. That's right. So it's the opposite. It's the vector pointing in the opposite direction, same magnitude, right? Parallel with a different sense, like I was talking about last time. So good. So that's how you'd use the cross product formula. Works for most. There is another way to do this that's a little bit more, I don't even know if concise is the right word. So we'll do the same vectors. But I got to explain something to you in a very hand-wavy way. I don't do this all the time. But there's a famous teacher. His name was Herb Gross. I don't know if you guys have ever heard of him, but he was a lecturer at MIT. He taught at Onondaga Community College. He's a legend among a lot of math professors. He was a funny guy, and he taught calculus. And he said, for the determinant, if you were to have the person who invented the determinant list off the reasons on why it was important and why it was invented, and you heard him mention that, was going through this list, and you heard him say, oh, you can also use it for the cross product, he said you could start to sigh relief because he'd be towards the end of the list, because it's really one of the least important ways you can use the determinant. Okay, so don't walk away from this thinking that I know the determinant and I know how to use it. This is very much a technique that just happens to work for the reason of duality, which is that there's like crossover between linear algebra and multivariate calculus here. So what is the determinant from, if you probably played with matrices too in high school a little bit, but given a matrix A, B, C, D, the determinant of this thing, which we use these linear braces, the straight braces to represent that, is equal to AD minus BC for a 2x2. So, for a concrete example here, the determinant of this 2x2, 1, 2, 3, 4, is going to be 1 times 4 minus 2 times 3, which is 4 minus 6, which is negative 2. Now for a 3x3, this is where it gets a little more involved, and it's because it's trying to mimic what we just did above, right? They're going to be equivalent things. So to just give it to you straight, if you've got A1, A2, A3, B1, B2, B3, C1, C2, C3, what you do is you're going to take 3 mini determinants with that top row, okay? So you're going to look at A, you're not going to consider the row or column it's in, and take the determinant of the remaining entries, okay? So what I mean is you take A1, multiply it by the determinant of B2, B3, C2, C3. And then for the others, you do the same thing. For A2, you don't consider the row or column it's in, and you take the determinant of the remaining entries. So, and it's a minus here too. So it's minus A2, determinant of B1, B3, C1, C3. Of course, I didn't leave myself room, but I have an iPad. Magic. And then same thing for the last one, right? Don't think about the row or column this is in. Take the determinant of plus A3, determinant of B1, B2, C1, C2. And from there, you'd do out these determinants, which you know how to do. They're not too bad. And just multiply them by that scalar A. A1, A2, A3, right? Because those are all just numbers. They're no longer vectors. So how does this translate to vectors? Great question. I'm glad you asked. So if we take that first row to instead be I hat, J hat, K hat, and we again take A1, A2, A3 as our A vector. Our B vector is B1, B2, B3. And again, order does matter here. and we place them in the bottom two rows, then what we'll do is the same thing, except it's I hat with the determinant of these. All right, so that's A2, A3, B2, B3, minus J hat times the determinant of what? Well, don't consider that or this. It's A1, B1, A3, B3. Something's going on with this pencil here. Do you need to sharpen a digital pencil? Is that a thing? Didn't think so. A1, A3, B1, B3, plus K hat, and again, the rows and columns that it's not in, A1, A2, B1, B2. So then what does that work out to be? Well, you do the difference of the crosses, right? That's the determinant. So it becomes A2, B3 minus A3, B2, I. Minus A1, B3 minus A3, B1, J hat. Plus A1, B2 minus A2, B1, K. So that's how we do the cross product for these two guys. So I'll write this in up here. Make sure you do that too. A cross B is this 3x3 determinant. All right. So I'm not going to have us go through that same example because I think you see the entries are exactly the same now, right? But how we get them, this can be a little bit nicer to work with if this process felt a little bit better. You know, you can remember this. Key tip, pro tip, people always forget this minus, okay? So to remember this minus here, I'll just highlight it like that. That sign matters. Okay. Everybody with me so far? Okay. Any questions at this point? Okay, so this is the process. It ends in what? Is this a scalar, vector, some otherworldly number we've never seen before?
Vector.
This is a vector. That's right. And again, I keep quizzing you on that because it's not always super clear if something's a vector or a scalar, especially when formulas get complicated. And especially when you have two different types of multiplication where one ends in a different type of number than the other one, right? So just to say that. Some nice properties of the cross product. Again, these will come in handy for solving problems. Refer back to them when you're, maybe stuck on a problem involving cross product. Could I represent it in a different way, right? Would reversing the orientation help me? Would distributing it, right? So the first is that, which you know already. Let's use A and B. We've been doing that the whole time. A cross B is the same as the opposite of B cross A. Very important. A cross B plus C. So again, vector sum results in what? Vector, right? A vector sum results in a vector. You just add the components together. You still get a vector, a resultant vector. And so A cross that makes sense. And so what it's going to end up being is actually A cross B plus A cross C, which is nice. So you can kind of see, it distributes over addition, over vector addition. So it's kind of close to multiplication. What else? If we have a scalar times some vector A, and I cross that with some vector B. This is the same as it's like the associative property of a scalar multiplication. It's the same as A cross scaling up B by C, or it's the same as scaling up the whole cross product. Okay, so scalar multiplication is commutative. Okay. And here's a weird one, which if you want to chase down, enjoy. Which is that A dot B cross C is the same as A cross B dot C. Now that is not obvious at all, okay? But I'm writing it here in case it comes in handy. And it'd be fun to just chase down the algebra too. Oh. I apologize to your eardrums personally. That was Ari, and she loves cross products. Okay. Also, she loves my wife more than me. That's why she freaked out. Okay. So we've got these nice properties. Couple additional ones that are really nice to have in the back pocket. The first is the following. If I have three vectors in R3, and I'm going to try to sketch this out as best as I can. If I have some vector A, I have another vector B, and I got another one kind of in the back there, C. You can see that this is like the corner where these tails meet. This is like the corner of some three-dimensional shape. I'm kind of putting this one in the background back here. And so if we do some translations on all of these and draw some not too terribly bad parallel lines. I think this should be a little bit more like this. Okay, we've got this slanted box. You seeing that? Maybe it's a little too abstract. Something like that. Might be hard to see too on the prompter. Okay, something like this. This shape is called a parallelepiped. Parallelepiped. Okay. So next time you're at a party, you can impress everyone there that you know that. And the volume of this thing is actually given by the magnitude of A dotted with B cross C. And again, there's some cool geometry to chase down in here. But this is what we call the scalar triple product. And it's not. There might even be a proof of this. In the text. Yeah. Page 859. There's a brief coverage. If I have time, I want to actually show you guys this thing. So I'll make a separate video for it. But for now, the volume of this is the magnitude of this. Obviously, the volume would be negated if the order is reversed on the cross product. Okay. So why this is helpful for us is that if I could determine that the volume of this thing were 0, what would we know?
Would that mean that the vectors are all on the same plane?
Yeah.
Or 0.
Or they're all 0. That's right. So it would mean they're either all 0 or they're all coplanar, which means they're living in the same plane, right? There's no rise off of that plane from any of them to create this parallelepiped, right? So if volume equals 0, we would know that A, B, C all lie in the same plane, which we call coplanar. Planar. Or that they're all 0. The 0 vector. So let's do that. Let's test that out right now. Give you a chance to recall the dot product, practice the cross product, and test out this new idea. Oh, I switched these up. Hold on. There should be a -1 and a +4. Okay, and vice versa, right? We know that if it's non-zero, that they're not coplanar. So give this a shot. At least get it set up. This doesn't seem right. So that's what, 18 negative 36 negative 18. -36 0. Oops. Yeah. Should be 0. Yes. Okay. So it should be 0. Now, the one thing that was a little cruel about this problem, but I did want you to practice both of these at once, is that this scalar product, the scalar triple product, actually has one additional nicety to it, which is that this is actually equivalent to if you were to just take the determinant with A as the first row, like this, okay? So you could have done it without the I, J, and K carried through those operations, it would have ended up with 0 as well, okay? And that'll be the same every time. So you can have that in your back pocket. Again, when is this useful? To find the volume of this thing, this parallelepiped. And so should you need to do that, this is the way to do it. And to also see if 3 vectors are coplanar, right? If the volume of this shape is 0, then you know these vectors all lie in the same plane. And again, while this might be a fair amount of work to check, it's much less than to get through setting up a triple integral and then find out all these things were in the same plane to start with, right? So, and that's not even the most important example you'd use it, but we have these tools like that to help us quick check what's happening with these vectors, because we might not be able to visualize it super easily by just sketching it. Okay, so this is 0, so that means that A, B, C are all coplanar, lie in the same plane. All right, 2 more facts. Cross product facts. So the first is that the cross product is 0 if and only if. You'll see me write this a lot too. I don't know if you've seen this elsewhere. If and only if. I'm not misspelling if. It's shorthand for a two-way conditional, right? This implies that and this implies that. So the cross product 0 if and only if A is parallel to B. Right? Why is that? Well, any other way, we said that the magnitude of A cross B is the area of the parallelogram, right? Where this is length A, this is length B. So if they're parallel vectors, that thing's going to have no area, right? So that's one, and one that you could probably solve and figure out on your own is that the magnitude of A cross B again, as long as we're talking about the right orientation, where I've got A and B over here, where B is to the left, and this is the angle of rotation, that this magnitude of the normal vector that's, shooting out here, this thing is equal to magnitude of A, magnitude of B, times the sine of theta. Because why? Because it's equal to the area of this parallelogram. And so you can draw in the altitude here and get that this must be, right, B sine theta times the base. That's this height here times the length of the base. That's just the area of the parallelogram. And again, it's important to note that you're talking about the smaller angle between the two. Because otherwise it flips the sign. It's a signed area. Right. Thought there was one more I had for you. No, I think that's it. To know, too, that the parallelepiped, the volume of that is at the heart of some of Kepler's laws of motion, which we'll hopefully have a chance to check out later in the course. So that is like a physical application. It's not just to see if things are coplanar. A lot of these things are fundamental operations to some of the most important equations that are out there. Okay, and again, the cross product, the way we calculate it here, is very much specific to R3, but the dot product scales to Rn, right? So n-dimensional vector spaces have the dot product. And so they generalize to these things called the inner and outer products, okay? So just to know that we're playing with some pretty powerful tools, and that should feel pretty cool. So I'm going to leave you with that. Do we have to go play on your homework? Do we have questions on anything covered today? Anything coming up? I'm going to put your problem set out today, and it's going to cover, I'm going to put it out for a week, so it'll be due a week from today, and it will cover up to and including the cross product. Okay, so there will be some cross product questions in there. What I'm experimenting right now with is it will pull a pool of questions. It will pull from a pool of questions is a better way to say that. And if you don't like how you did, you can retake it a couple times. I think you'll have 3 attempts on it. And again, these are relatively low stakes. They are more interesting problems, more challenging problems typically than what you're seeing in the textbook and what you're seeing in the other online practice problems. But they're not meant to be a punishment or anything like that. And reach out with any place you get stuck. I'll be, I really am trying not to check email during the weekends. It's just a healthy practice, I think, for everybody. But I do check my email and discussion posts several times throughout the day. So if you ever, have a question, just make sure you get in touch. It's the committee work I don't like getting back to people on. Questions about calculus, you guys get first priority, okay? So, all right, that's it from me. You guys have a great weekend. If you have questions, please hang out. Otherwise, we'll see you next time. Have fun.
Have a good one.
Take care. Thanks, you too.
I got a question, Sean.
Sure.